We tend to think of graph algorithms as this really abstract academic thing, but they're not. They're actually the secret sauce running the world all around us, from your GPS to your social media feed. Once you start seeing systems as just a collection of connected dots, a graph, a few really fundamental questions just naturally pop up.
So you start with the most basic question of all, right? Is a connection even possible? Can a packet of data get from this server to that one? Can I actually get from my house to the airport? It's a simple yes or no, but it's the absolute foundation for everything that comes next.
Okay, so if the answer is yes, if you can get there, the next question is pretty obvious. What's the most efficient way? We don't just want any path, we usually want the best one. And right now, we're not even talking about traffic or tolls, just the fewest number of steps, the most direct route possible. And that brings us to the final, and maybe the most complex question. This is where optimization gets really, really interesting. Because here, cheap doesn't just mean money. It could be the fastest time, the least amount of fuel, or the most reliable connection. And that's the whole point, isn't it? These aren't just random questions we're asking. They are the core problems that graph theory was built to solve. And for each one of these questions, there's a set of powerful, super reliable algorithms designed to give us the answer. So here's what we're going to do in this explainer. We're going to start with those three core problems. Then, we'll look at the clever ways we can figure out if a path even exists in the first place. After that, we'll dive into the really juicy challenge of finding the best path. We'll even explore what happens when our trusted tools fail us. And then finally, we'll see how this all comes together to pretty much run the world. All right, let's start by simplifying things a bit. You might think there are endless problems you could solve with graphs. From analyzing complex networks to global supply chains. But what's so fascinating is that pretty much every single one of them can be boiled down to just one of three key questions. First up, you've got reachability. Is a connection even possible? Can I get from A to B at all? Second, paths. Okay, what's the actual sequence of steps to get there? And third, costs. Now that we know all the possible paths, which one is the best, based on something like time or distance or money? Pretty much everything else is just a spin on one of these. All right, let's dig into that first one, reachability. It sounds super simple, but honestly, it's the bedrock of everything else. Before we can even start thinking about the best route or the cheapest option, we have to answer that first fundamental question. Is a connection even on the table? So reachability is purely about existence. We don't care if the path is long or short, efficient, or totally roundabout. We just need to know if it exists. And the two big names you'll always hear for this are breadth first search, or BFS, and depth first search, or DFS. They're like two totally different strategies for exploring a map. And how they explore is totally different, and it's super important. Think of breadth first search like ripples in a pond. It checks all of its immediate neighbors first, then all of their neighbors, just spreading out one layer at a time. And that methodical approach guarantees it'll find the shortest path in terms of raw hops. Depth first search, though, that's more like trying to solve a maze. It picks one path and just goes deep, all the way to the end, before it backtracks. This makes it amazing for figuring out the overall shape of the graph, and for spotting for just going in circles. And this brings us to a really key engineering truth. Choosing between BFS and DFS isn't random. It's a very deliberate decision based on what you need to find out. Do you need the most direct route, or do you need to know the overall structure? The question you're asking determines the tool you use. Okay, so we've established that we can get there. Great. Now the question gets a lot more interesting. We're not just asking if anymore. Now we're asking how much. This is where we make the leap from simple reachability to true optimization. And look, cost can mean pretty much anything you want it to. It could be the literal distance for GPS, the lag time in a network, or even financial risk in a trading system. The two heavy hitters for solving this kind of problem are Dijkstra's algorithm, which is incredibly fast, but has one big limitation, and the Bellman-Ford algorithm, which is a bit slower, but way more flexible. But here's the catch, and it's a big one. Every single optimization algorithm is built on a set of assumptions about how the world works. Dijkstra's, for example, assumes all costs are positive. You can't travel negative distance. And the moment that assumption gets broken, the algorithm can flat out give you the wrong answer. So this leads to a really interesting question. What happens when these amazing algorithms just break? Let's look at why a famous algorithm like Dijkstra's completely falls apart when it runs into something weird, like a negative cost. Imagine you're planning a trip, right? You use an app and it finds the cheapest route. But then a friend tells you about this bizarre shortcut that doesn't just get you there, it somehow pays you to take it.
like a refund. That's exactly what a negative edge in a graph is. So here's the problem. Dijkstra's algorithm is an optimist. Once it finds what it thinks is the cheapest path to a point, it locks it in and never looks back. It assumes it can't get any better. But that weird refund shortcut could suddenly make a path that looked expensive the cheapest one of all. Dijkstra's core assumption is violated, and its answer can no longer be trusted. And that just hammers home another huge engineering lesson. Knowing what an algorithm can't do is just as important as knowing what it can. Its correctness is directly tied to its rules. You have to respect the constraints of the tool you're using, or you're going to get burned. Okay, so let's pull back from the theory for a second and bring this all together. Let's see how these abstract ideas are not just lines in a textbook, but are actually the foundation of the technology we use every single day. So let's break this down into a simple cheat sheet, right? If your question is simply, can I get there? Then you're going to use DFS or BFS. If you need the absolute shortest path in terms of the number of stops, no questions asked, BFS is your best friend. For the cheapest path, where all the costs are positive, no weird refunds, Dijkstra's is the way to go. But if you do have those negative costs in your system, you need the power of Bellman 4. And make no mistake, this stuff is everywhere. Every time you use Google Maps, you're using a cost-based pathfinding algorithm. When your computer installs software, a dependency graph is being solved to get everything in the right order. Recommendation engines, fraud detection, even AI knowledge systems, they are all at their core powered by these exact concepts. When you really step back and think about it, graphs teach us something really profound about how systems work. The structure itself, the way the dots are connected, that's what defines the absolute limits of what's even possible within that system. And how we decide to explore that structure, our traversal strategy like BFS or DFS, that defines what we can even understand about it. And finally, the costs we assign to those connections, whether it's time, money, or risk, well, that's what ultimately defines the choices we make. So what's the big takeaway here? It's that learning to reason about paths and costs and reachability, it isn't just about computer science. It's a really powerful way to think about and understand complexity in just about any system you can imagine.